The Benelli M4 appeared on evaluation ranges in 1998 as an answer to a question most engineers had stopped asking. Could a semi-automatic shotgun truly be universal? For decades, the hardware industry had accepted a quiet compromise. Gas-operated platforms existed, but they demanded specific ammunition, regular maintenance, and environmental consideration. They were tools for controlled circumstances. The military needed something different, a piece of equipment that functioned regardless of load selection, cleaning schedule, or field contamination. When Bruno Civolani's prototype arrived at the U.S. Joint Service Combat Shotgun trials, it carried no revolutionary appearance. Externally, it resembled other tactical tools: black polymer furniture, ghost ring sights, extended magazine tube. The innovation lived entirely within the first 8 inches of barrel length, invisible until disassembly. Evaluators initially approached it with institutional skepticism. Gas-operated systems had promised reliability before. They had failed before. The trial protocol was designed around that history of failure. Test equipment would discharge thousands of rounds, representing every ammunition category, from light 2-3-4-inch loads to heavy 3-inch magnums, from standard buckshot to specialized breaching rounds. Between sessions, the platforms would be exposed to sand immersion, saltwater spray, and mud contamination. No cleaning would be permitted until a total mechanical breakdown. Previous gas-operated designs typically failed within the first 500 rounds, their gas tubes choked with carbon residue or their action springs weakened by pressure inconsistency. The M4 behaved differently from the first magazine. Where other semi-automatic platforms demonstrated hesitation or harshness, short-stroking with light loads or battering their internal frames with heavy ones, the Benelli cycled with mechanical neutrality. The action opened and closed with identical timing, regardless of shell power. Evaluators noted this immediately. It wasn't dramatic. It was eerily consistent. By the 1000th round, competing designs had been withdrawn for maintenance. By the 2000th, only the M4 remained functional without intervention. The platform's behavior under contamination proved even more anomalous. After mud immersion that would render most equipment inoperable, the M4 required only a brief drainage shake before resuming operation. The carbon buildup that compromised conventional gas systems seemed unable to accumulate anywhere the M4's internal mechanisms operated. The engineering question shifted. This wasn't about whether the platform worked. It was about understanding why it worked when fundamental design theory suggested it shouldn't. The answer resided in decisions Civolani had made years earlier, decisions that rejected 90 years of gas-operated orthodoxy in favor of a principle so simple it had been overlooked. Put the gas system where gas behaves most predictably, and let physics handle regulation automatically. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far. And stay with us for the next chapter. Bruno Civolani faced the problem in 1995 with institutional pressure mounting. Benelli had built its reputation on the inertia-driven system, a brilliantly simple mechanism that used recoil energy rather than gas to cycle the action. It required no gas ports, no pistons, no tubes. It was mechanically pure, but it had limitations. Inertia systems demanded rigid operator positioning and couldn't reliably cycle lightweight target ammunition. For sporting use, this was acceptable. For military adoption, it was disqualifying. The company needed a gas-operated system, but every conventional approach carried inherited problems. Traditional rifle-style gas operations used a long tube running beneath the barrel, drawing combustion gases rearward to drive a piston or bolt carrier. In certain platforms, this worked adequately. In shotguns, it created cascading failures. Shotgun ammunition varied wildly in pressure output. A light target load might generate 7,000 psi. A heavy magnum could reach 12,000 psi. A single gas system optimized for one pressure range failed significantly with another. Engineers typically solved this through adjustable gas blocks, mechanical valves that could be manually tuned for different ammunition types. This satisfied civilian sport enthusiasts who used consistent ammunition. It was useless for tactical operators who might switch between breaching rounds, buckshot, and less lethal projectiles within a single engagement. The platform needed to self-regulate, but no one had demonstrated a reliable method for automatic gas regulation in shotguns. Civolani approached the constraint differently. Instead of trying to regulate variable pressure after gas entered the system, he questioned where the gas was being captured. In conventional designs, gas ports were located mid-barrel, where pressure varied dramatically depending on ammunition. He recognized that all shotgun loads, regardless of initial pressure, produced similar gas behavior at one specific point, near the muzzle, where combustion was complete and pressure had stabilized. He also questioned the single-piston paradigm. One large piston required high gas volume to function, which meant capturing gas early in the barrel's length, where pressure variation was maximum. Two smaller pistons could divide the work, requiring less individual gas volume and permitting gas capture farther forward, where pressure was more consistent. The concept was mechanically counterintuitive. More parts typically meant more complexity, but the mathematics supported it. Dual pistons operating in parallel created functional redundancy. If one received insufficient gas, the other compensated. The proposal met internal resistance. Benelli's leadership had invested heavily in promoting inertia-operated simplicity as superior to gas-operated complexity. Civolani was now suggesting they build a gas system more complex than competitors. The argument that eventually prevailed wasn't about part count, it was about contamination resistance. Gas tubes, the primary failure point in conventional systems, wouldn't exist in Civolani's design. The gas ports, pistons, and operating rods would all reside in the barrel's forward section, the hottest zone, where carbon couldn't accumulate. The system would be self-cleaning by virtue of placement, not by special coatings or materials. The auto-regulating gas-operated system operated through positional logic rather than mechanical complexity. In a conventional gas-operated platform, combustion gases traveled rearward through a tube, driving a single piston that unlocked and cycled the internal mechanism. The tube became the system's vulnerability, a long, narrow passage where carbon residue accumulated with every discharge, progressively restricting gas flow until the equipment short-stroked or failed entirely. Cleaning the gas tube was mandatory maintenance for reliable function. Civolani eliminated the tube. His design placed two stainless steel pistons in cylinders machined directly into the barrel, just forward of the chamber. Each piston connected to the bolt carrier through short operating rods that ran alongside the magazine tube. The gas ports that fed these pistons were drilled near the muzzle, approximately 12 inches forward of the chamber. When the platform was activated, combustion gases traveled down the barrel, pushing the projectile column ahead. As the contents exited the muzzle, residual gases vented through the two ports simultaneously, driving both pistons rearward. The elegance emerged from gas behavior at that specific barrel location. Near the muzzle, all shotgun ammunition, regardless of initial pressure differences, produced gas in a relatively narrow pressure band. Light loads generated lower peak pressure but burned their powder more completely by the time gases reached the ports. Heavy loads generated higher peak pressure but had already vented most excess energy through the muzzle. The result was functional convergence. Different ammunition types produced different absolute gas volumes, but similar effective force at the piston location. The dual piston arrangement provided automatic compensation. With light ammunition, both pistons contributed their full stroke to cycle the action. With heavy ammunition, each piston required less individual travel to achieve the same internal velocity, and excess gas vented forward through the muzzle rather than battering the internal frame. The system self-regulated without valves or adjustable components, because the regulation occurred through positional physics rather than mechanical intervention. The operating cycle itself was conventionally linear. As the pistons drove rearward, they pushed the carrier backward, extracting the spent shell and resetting the mechanism. A recoil spring positioned around the magazine tube stored energy from the rearward motion, then drove the carrier forward, stripping a fresh shell from the magazine and chambering it. The entire cycle completed in approximately 40 milliseconds, identical timing across the full ammunition pressure spectrum. What distinguished the Argo system wasn't faster cycling or higher reliability in pristine conditions. It was immunity to the progressive degradation that compromised other gas-operated designs. The short gas travel path meant carbon never accumulated in sufficient quantities to restrict flow. The forward piston location meant operating temperatures remained high enough to burn off residue continuously. The stainless steel pistons required no lubrication, eliminating another contamination vector. The system didn't resist fouling. It prevented fouling from having anywhere to accumulate. During development, Civolani tested this principle deliberately. He operated the prototype for 500 rounds without cleaning, then disassembled it to examine carbon buildup. The gas cylinders showed superficial discoloration, but no restriction. The pistons showed no scoring or residue adhesion. The operating rods showed minimal wear. The platform had cleaned itself through operation, exactly as positional theory predicted. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The revision process began with a hurdle, though not of the hardware itself. Early prototype testing in 1996 revealed that Civolani's Argo system functioned flawlessly under controlled conditions, but encountered bureaucratic resistance within Benelli's engineering review process. Senior engineers questioned whether customers would accept a gas-operated Benelli after years of marketing inertia systems as inherently superior. The company had built brand identity around simplicity, fewer parts, fewer problems. Now, Civolani was proposing they embrace a design with more components than competitors' gas systems. The breakthrough came through demonstration rather than argumentation. Civolani arranged a comparative test using a competitor's gas-operated shotgun and his Argo prototype. Both platforms discharged 1,000 rounds under identical conditions. A mix of light target loads and heavy magnum shells, no cleaning permitted. The conventional gas shotgun began short-stroking after 600 rounds, its gas tube visibly clogged with carbon. The Argo prototype completed all 1,000 rounds without malfunction, then continued for another 500 rounds while company executives observed. This performance convinced Benelli's leadership to pursue military evaluation, but it also exposed a different engineering challenge. The prototype's reliability came at a weight penalty. The dual-piston system and reinforced barrel required additional steel, making the platform heavier than competitors. For military adoption, weight mattered. Personnel already carried excessive loads. A tool that added unnecessary ounces might be rejected despite superior performance. Civolani's team spent 8 months redesigning the receiver and barrel assembly, using aerospace-grade aluminum alloys where stress analysis permitted and optimizing steel placement where strength was critical. They reduced weight by 18% without compromising the Argo system's operating principles. The final production design weighed 7.8 pounds unloaded, competitive with manual action platforms while offering semi-automatic capability. The formal U.S. military evaluation began in 1998 and immediately differentiated itself from previous trials. Instead of focusing solely on accuracy and performance, evaluators emphasized sustained function under adverse conditions. Test protocols included immersion in sand, mud, and salt water, followed by immediate operation without cleaning. Equipment was frozen to sub-zero temperatures and heated to desert extremes. Ammunition varied systematically between minimum and maximum pressure specifications. The Benelli M4 wasn't the only gas-operated entry, but it was the only design that maintained function through all environmental protocols. Competing platforms consistently failed after contamination exposure, requiring disassembly and cleaning to restore operation. The M4 required only drainage of bulk contamination, sand or mud poured from the action, before resuming operation. Evaluators documented this behavior with mechanical precision, noting that the platform's function actually improved slightly after the first 100 rounds, as if the system needed break-in rather than maintenance. The U.S. Marine Corps formalized adoption in 1999, designating the platform MTO-14. The decision wasn't based on superior firepower or accuracy. Manual action shotguns matched those metrics. It was based on operational endurance, under conditions where maintenance was impossible. The Argo system had proven that gas operation could exceed manual reliability if the gas system was positioned where physics prevented fouling, rather than where mechanics attempted to manage it. The final curiosity emerged, not during development, but during deployed use, when maintenance personnel noticed something unexpected in reports. The MTO-14 platforms returning from extended field exercises showed less internal wear than predicted. Units that had discharged thousands of rounds in desert environments where sand infiltration typically destroys gas-operated equipment arrived back at maintenance facilities with their gas systems cleaner than when issued. The carbon buildup that normally required chemical solvents and wire brushes was absent. Initial reports assumed operator error. Perhaps personnel were cleaning the equipment but failing to document maintenance properly. Inspection proved otherwise. The gas cylinders, pistons, and operating rods showed usage evidence, finish wear, heat discoloration, but no carbon accumulation. This contradicted every gas-operated platform in the inventory. Standard carbines required frequent gas system cleaning. Light machine systems required near-constant maintenance to prevent gas tube failures. The MTO-14 seemed immune to the contamination that compromised its counterparts. The explanation resided in Civolani's original design insight, but its implications hadn't been fully understood until field data confirmed them. By placing the gas ports 12 inches from the muzzle, he'd positioned them in the barrel's thermal maximum, the zone where gases remained above 800 degrees Fahrenheit during sustained use. At these temperatures, carbon particulates couldn't form deposits. They remained gaseous or burned off immediately. The stainless steel pistons operating in this thermal environment never cooled enough for residue adhesion. The effect amplified during sustained use. Where conventional gas systems degraded progressively, each shot depositing microscopic carbon layers that eventually choked the tube, the Argo system actually stabilized after its first 100 rounds. The initial sequence seasoned the metal surfaces, creating a microscopic oxide layer that became more resistant to adhesion with use. The equipment literally became more reliable through operation, rather than less. This behavior solved a problem the military hadn't explicitly stated in its evaluation criteria, but which dominated actual field logistics: equipment maintenance under resource scarcity. In deployments, lubricants, solvents, and cleaning time were limited commodities. A tool that required minimal maintenance wasn't merely convenient, it reduced logistical burden and extended operational tempo. The MTO-14 could function for weeks without cleaning, not because it resisted contamination through special coatings, but because contamination couldn't form where physics prevented it. Civolani had designed the system around ammunition versatility, and discovered, almost accidentally, that positional optimization solved the contamination problem simultaneously. The same forward gas port location that enabled pressure self-regulation also enabled thermal self-cleaning. The same dual piston arrangement that compensated for ammunition variance also distributed wear symmetrically, preventing stress concentration. The system's reliability wasn't engineered through complexity, it was inherent in geometric relationships between heat, gas flow, and mechanical motion. The final curiosity confirmed the original principle. The best engineering doesn't fight entropy. It positions mechanisms where entropy has minimal effect. Civolani hadn't made a platform that resisted fouling. He'd made a platform where fouling couldn't occur. The Benelli M4's legacy isn't measured in units produced or operations completed. It's measured in the principle it validated, that revolutionary reliability comes from eliminating failure modes rather than hardening against them. For a century, gas-operated design followed the traditional paradigm: capture gas mid-barrel, route it through a tube, use it to drive a piston. Engineers spent decades optimizing this configuration with exotic materials, precision manufacturing, and elaborate maintenance protocols. The improvements were incremental, and the fundamental vulnerability remained unchanged. Civolani's contribution was recognizing that the vulnerability wasn't solvable within the existing framework. The gas tube, regardless of metallurgy or coating, would always accumulate carbon, because it existed in a thermal gradient, hot near the chamber, cool near the gas block. Carbon deposition was inevitable physics. The solution wasn't better materials. It was eliminating the tube entirely by relocating the gas system to where temperature remained uniformly high. This design philosophy influenced subsequent hardware development beyond shotguns. The Argo principle, that mechanical simplicity emerges from positional optimization rather than part reduction, appeared in rifle designs, machine systems, and even larger recoil mechanisms. Engineers began questioning conventional component placement, asking not whether a system could be made simpler, but whether it could be positioned where physical laws worked in its favor. The M4 served the U.S. Marine Corps for 2 decades as the primary tactical shotgun, deployed in every major operation from 1999 forward. It functioned in mountain cold and desert heat. It discharged breaching rounds, buckshot, and less lethal munitions without adjustment. Operators reported that the platform's most notable characteristic wasn't its effectiveness, which matched conventional manual actions, but its invisibility. It functioned so reliably that users stopped thinking about it as a mechanical system requiring attention and began treating it as a simple tool that always worked. This operational transparency represented Civolani's ultimate achievement. The Argo system's complexity, its dual pistons, forward gas ports, and thermal optimization disappeared from user experience. The operator never adjusted gas settings because none existed, never cleaned the gas system because carbon couldn't accumulate, never worried about ammunition compatibility because the platform self-regulated automatically. The engineering sophistication became invisible precisely because it was effective. In 2018, the service began transitioning to newer designs, not because the M4 had failed, but because 2 decades of service had proven the Argo principle completely. Subsequent designs incorporated forward gas positioning and thermal self-cleaning as default expectations rather than innovations. The Benelli M4 had demonstrated that gas-operated reliability could exceed manual operation, provided the gas system was positioned correctly. That demonstration became permanent institutional knowledge. Bruno Civolani's final curiosity, that equipment cleans itself when placed where physics prevents contamination, evolved from observation to principle to expectation. The Argo system proved that the most elegant engineering solutions don't overcome physical constraints. They position mechanisms where those constraints cease to apply. That lesson, validated through decades of field use, remains the Benelli M4's permanent contribution to engineering thought. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching. Would you like me to translate another technical script, or perhaps generate a detailed visual description of the Argo dual piston system for your video production?